Now let's start the discussion regarding isoelectric focusing, which is another electrophoretic method to separate protein samples. Although we have SDS page for separating protein sample that we have already discussed in our earlier videos. So now the question is why we have developed another electrophoretic method for separating proteins, right? So here the reason. Suppose this is a protein sample mixture, okay, and here your protein of interest is present, okay, which is in red color, okay. Along with that, it also contains another protein which is not your protein of interest but of same molecular weight, okay. Then how can you separate these two with the help of normal SDS page? Because we all know that SDS page separates protein on the basis of their molecular weight, right? So SDS page cannot separate these protein samples, right? So that is the reason, except molecular weight, we have to take another physical method under consideration or another physical characteristics under consideration. So here we have taken isoelectric point as our consideration, okay. So now let's start our discussion regarding what is the isoelectric point. So before going to talk about isoelectric point, I am going to discuss with you how protein charge is determined by her, or how the local environment in which our protein is present determines what will be the charge of that protein, okay. So I hope that if I clear the concept regarding this with the help of amino acid, then you can easily interpret what is going on in case of protein. So I have drawn here a glycine amino acid, and remember, when the local environment is acidic, that simply means in the local environment there are too much H plus ion present, okay. And whenever there are too much H plus ion in the environment, this H plus ion simply react with NH2 and makes this NH2 protonated, or that is NH3 plus, okay. So one thing you can keep in your mind, that whenever we are in acidic condition, or whenever the protein is in acidic environment, so in the acidic environment there are 2 plus H plus ion present, and in the presence of that H plus ion, this NH2 simply react with H plus and gives you NH3 plus. So in the acidic environment, your protein is positive, your amino acid is positively charged, okay. Similarly, in basic environment, remember, in the local environment of the pH, when basic, that means in that environment there are too much OH minus ion present, okay. And in the presence of too much OH minus ion in the environment, the COOH group will simply donate a hydrogen, okay. This hydrogen going to react with OH minus and gives you water. That means this hydrogen simply neutralize the OH minus and gives you the water, and amino acid remains deprotonated. The condition is just like that. COOH and OH minus is present in the environment, so H will be donated by COOH and convert the OH minus into H2O, and in turn the COOH remains COO minus and remain the amino acid negatively charged. Now we all know that protein is nothing but a polymer of amino acid, right? 50 to 100 amino acid joined together with the help of peptide bond and leads to the formation of protein. So the thing that is going on in case of peptide, in case of amino acid, will also applied in case of our protein also, right? Because it is generally made up of amino acids. So that is the reason. Same funda will be applied in case of protein. If your protein is located in an environment that is acidic, then it will become positively charged, and if your protein is located in an environment that is basic, your protein will be negatively charged, okay. Now, as we are telling that protein's charge is depending on the pH of the environment, there will be a pH point in which the protein positive and neutral charge, the amount of positive or neutral charge in the protein is exactly equal. Okay, that means the net charge of the protein becomes neutral. Let me write, that means amount of positive charge is exactly equal to the amount of negative charge. Okay, that is the thing, and that pH value is commonly known as pi or isoelectric point. In that point, the protein will not migrate towards any of the electrode. Why? Because remember, depending on what is the net charge, it will either migrate to the cathode or either migrate to the anode, right? If your protein is negatively charged, then it will migrate towards the anode, and if it is positively charged, it will migrate towards the cathode, right? So that is the idea. So here we are going to use the differences in isoelectric point. So as we are using differences in isoelectric point, so it is obvious that isoelectric points are varies among proteins, right? And it is obviously isoelectric point usually lies between pH 3 to 12. Okay, you can find isoelectric point of every kind of protein between 3 to 12, and more specifically most of the important proteins isoelectric point lies between 4 to 7. Okay, now so remember another simple trick, that in case of acidic and basic amino acid, right, because we have some acidic and basic amino acid that can be also constituent of protein, where side chain also contain acidic or basic group, right? In case of aspartic acid, we have COOH in the acidic group, in the side chain. In case of lysine arginine, we have amino group in the side chain, right? So in such cases, we have to take the charge of the side chain also under consideration. Okay, so remember one thing, if your protein acidic group, even if your protein's acidic group is greater than the basic group present, then your protein's pi will be lower and this protein will be considered as acidic. Again I am repeating that suppose your protein contains 3 COOH group and 2 NH3 group, that means acidic group is greater than the basic group, so your protein's pi will be low, and in turn your protein will be regarded as acidic protein. Okay, similarly if your protein, and when the basic group out the number of the acidic group in a protein, the pi will be high and the protein will be classified as being basic. Okay, so that is the thing. How can you determine? Also we have the standard formula to determine pi. If you want, then I will discuss these two. Okay, so thick. Okay, now so how can we use these differences in isoelectric point to separate protein on the basis of them? So our first goal will be here to generate a pH gradient on the polyacrylamide gel backbone, because remember the main basic is the same. We are again here using polyacrylamide gel, but we have along with polyacrylamide gel generating a pH gradient. Okay, so when during the migration of protein towards cathode or anode, because remember here we are not going to use SDS, that means all proteins are not going to migrate towards the anode, right? So during their migration toward anode and cathode, as we have generated pH gradient, they will find a point that is exactly equal to their pi and they will stop there, right? And in that way a sharp separation or focused separation can be done with the help of this technique, and that is why the name isoelectric focusing. Okay, this isoelectric focusing can separate protein or resolve protein having difference in pi values of 0.01. Okay, that means proteins with differences in one charge can be separated with the help of this isoelectric focusing technique. So as I have told you that we have to generate a pH gradient, so our first goal will be to generate pH gradient, right? So pH gradient can be generated with the help of two methods. One is carrier ampolyte method and another one is immobilized gradient strip method. Okay, immobilized pH gradient strip method and another one is carrier ampolyte method. So what we are doing here in case of carrier ampolyte is nothing but polycationic and polyanionic molecules. Okay, so we will simply add in the polyacrylamide backbone the carrier ampolyte mixture, and when we will generate voltage, then the carrier ampolyte with higher pi value will migrate towards the cathode. Okay, because higher pi value will have high positive charge. Okay, and carrier ampolyte with a lower pi value will migrate towards the anode containing the most negatively charged, and all the remaining carrier ampolytes that are present below or that are present behind, sorry for that, all the carrier ampolyte that are present in between the highly positively charged carrier ampolyte and highly negatively charged carrier ampolyte will align in between them depending on their pi value and generate a pH gradient for you. Okay, and this pH gradient will simply from pH 3 to pH 10 most of the cases. Okay, so as we have discussed that all the pi value of protein is generally lies between 3 to 12 and more specifically 4 to 7. So if we load our sample in between the carrier ampolyte mediated pH gradient, so we can easily separate them on the basis of their pi, right? So that is the idea. And again we can also use immobilized gradient strip where we will covalently grafting different buffer groups. Okay, and on the basis of the different buffer group we can create a pH gradient. Okay, so this is the two method that we can take under consideration now. So we have successfully generated the pH gradient. Okay, now what will be our job? So we have generated the pH gradient. Now we will add our protein sample in the middle of the pH gradient. Okay, remember one thing here, we do not create any kind of well. As you can see, I still do not mention any kind of comb here, right? So we are not going to use any kind of well here. We will simply add the protein with the help of soaking paper or any other thing in the middle of the pH gradient. Okay, so suppose this local environment is 7, here we have 3, here we have 10. In the protein mixture, when we will generate again voltage, okay, those protein sample whose pi value is 4 but it is located at the pi value 7, at the pH value 7, that means pi value is less than the pH of the environment, right? So that means pH of the environment is greater than the pi value, that means too much OH minus ion in the local environment. That means the pi value 4 containing protein becomes what? The pi value 4 containing protein become negatively charged here. Okay, so sorry, this will be the negatively charged. This is our pH 10 3 and this is positive charge. So we are discussing that here we have incorporated the protein and here a protein sample whose pi value is 4 but which is less than the pH of their local environment. That means local environment is basic, that means too much OH minus ion. So as a result our protein is negatively charged. So it will migrate in presence of the electric field towards the positive electrode, as we have incorporated positive electrode here. and during this migration it will find the pH value 4 here, and this pH value is the pI value for the protein, right? So it will become fixed here. Okay, again suppose another protein whose pI value is 8 but having same molecular weight with the pI value 4 containing protein, it will migrate here because here the pI value is greater rather than the your pH of the environment, and as pH value is lower than the pI value, that means the pI 8 containing protein is positively charged. Okay, because here the local environment is acidic for it. So in presence of the positively charged protein will migrate towards the negatively charged electrode, and during this migration it will find the pH value 8, and as it is the pI value for that protein, it will stop here. So we can simply separate two same molecular weights containing protein by the help of isoelectric focusing. That is the basic idea about isoelectric focusing. Okay, so now we have two kind of isoelectric focusing. I am just writing IEF. So one is native isoelectric focusing. As the name suggests, here we are keeping the protein structure and biological activity intact, right? But and native IEF is not used widely. Why? Because in case of native IEF, most of the protein are not soluble at low ionic condition or at a pH value which is very close to their pI. Okay, so instead we are using denaturing IEF, where we are using high concentration of urea. So remember one thing, urea is here is the denaturant of choice, because urea is uncharged compound, and this urea will bind with the protein and solubilize them. Otherwise those protein are not soluble under IEF condition. Remember this, that why use of IEF, native IEF is limited, because that many protein are not soluble at low ionic strength or have low solubility close to their isoelectric point. That is the problem we are facing in case of native IEF. That is why we have shifted our separation in denaturing IEF in presence of high concentration of urea, which dissociate protein into individual subunit and abolishes secondary tertiary structure. Okay, that is fine because it is a denaturant. Along with the most important thing to choose urea is it is an uncharged compound that can solubilize many protein which are not soluble otherwise under IEF condition. Okay, so we have separated well. Now the question is, how can we detect them? So remember one thing, before washing, if you add Comasi blue, then we will end up with a gel which is totally blue, because don't forget that we are here using carrier ampulites, right, or immobilized buffer groups that we have grafted, right? So this immobilized buffer group or carrier ampulite, remember, can also take Comasi blue, so it will become stain. So how can you separate? Because here you are getting a gel which is completely blue. So for that thing, for the first goal of us will be to wash them. So we can easily wash them with the help of 10% volume by volume trichloroacetic acid, and after that separation we will after the washing we will use staining with Comasi brilliant blue. Okay, so that is how the detection can be done. After staining with Comasi brilliant blue, the separated protein will appear as blue color band, okay, which can easily be detected, and then you can easily separate your protein who are of same molecular weight but having differences in isoelectric point. Okay, that is how isoelectric focusing uses differences in isoelectric point by preparing a pH gradient with the help of carrier ampulite or different buffer group, that is immobilized pH gradient strip. We are separating our protein of same molecular weight. Okay, so that is how the entire process is going on in case of isoelectric focusing. We have another important gel electrophoresis lab that I am going to discuss with you some other day, that is So we are just attaching isoelectric focusing along with our SDS page, okay, to increase the resolution. So these two separation technique together called 2D gel electrophoresis. That means here we are taking two physical properties together under consideration. One is isoelectric focusing and another one is SDS phase. That is why the name 2D. We are going to discuss about this some other day. So I hope that this video will be helpful to you, and I am also let you to take a screenshot so that you can prepare this isoelectric focusing chapter well. So take the screenshot. Okay. So I hope that this video will be helpful to you, and if it is, please hit the like button, share with your friends and subscribe to my channel to get more videos like that. Thank you for listening to this class.